I have the pleasure to introduce our speaker today, Xin Li from the University of Glasgow, who's going to talk about ample groupoids, topological full groups, algebraic theory spectra, and infinite loop spaces. Please, Xin, go ahead.
Okay. Well, yeah, first of all, thank you very much for the invitation. It's a great pleasure to talk to you today. Yeah, so the title of the talk is what Willy said. Let me maybe give a quick outline of the talk. So the plan today is, so the talk mainly is about the class of groups called topological full groups. And these groups are constructed, if you want, from dynamics. So the first part of the talk will be about this class of groups. So I'll explain the construction and why these groups are interesting. And then, I'll come to the main results of the talk, which are about homology for these topological full groups. So I will present various results and some of the consequences. And then, we will see how much time is left. So I at least want to try to show you some of the key ideas and use that as an excuse to tell you more results. But let's see how far we get. Okay, so so groups of dynamic origin. To explain this, I first need to say what I mean by dynamics. And I want to view dynamics or interpret that in a very sort of broad sense. And for me, what I mean is really by dynamics, I mean topological groupoids. So let me give a quick introduction to those. Some of you have seen those, so it will be rather brief. So a groupoid, if you want, is a small category where all morphisms are invertible. But as the name suggests, you can think about the groupoid as being a group, but multiplication is not everywhere defined. So the groupoid elements you view as arrows pointing from an object called the source to an object called the range. And you identify objects with morphisms, so sending an object to its identity morphism. So you just talk about morphisms usually for groupoids. And then if you have this picture of these arrows, then intuitively it's sort of clear what conditions you need to be able to multiply two. So the range and source have to match up, and then you can form the product. And so with all this, you see that you have all sorts of operations. You have this inversion because every morphism has an inverse. You have multiplication, which is concatenation of arrows. And so altogether, this gives you the algebraic structure of a groupoid. But now we want to add some topology. So in addition, we assume that G is a topological space and that all these operations are continuous. Right. And then, so there is this G0, which is the unit space. So this is the subset of all objects, which we identify with the identity morphisms. And this subspace, I want it to be a very nice topological space. So that should be locally compact in Hausdorff. So maybe one slightly subtle thing is that I don't want the groupoid G to be Hausdorff as a whole, but I just want the unit space to be Hausdorff. This is so that you cover some of the interesting examples that come up. Okay. Maybe I can show you some examples. So the first one, I guess this is what people might call classical dynamical systems. So this is really just you have a group acting on a space by homomorphisms, and then you form the transformation groupoid. So as I said, you just look at the pairs, one group element, one point in the space. And in this picture, you view such a pair as an arrow pointing from your point X to the group element applied to X using the action. Okay, and maybe I'll show you another example. So this example is coming from symbolic dynamics, where we look at this shift map. So we look at one-sided infinite sequences, 0-1 sequences, and this shift map just shifts the sequence, so it forgets the very first or the 0th entry and just shift. So in contrast to the first example, this transformation is not invertible because you lose information whenever you shift. But nevertheless, you can construct groupoids also in that setting. So for this particular example, the groupoid will look like this. So elements are triples. X and Y are infinite sequences, one-sided. And then in the middle, this L minus K is an integer. And the restriction or the condition is that this integer can be split as a difference of two natural numbers, such that if you shift your X by K and your Y by L, then you get the same infinite sequence. So in other words, these sequences are shift equivalent. So up to finite shifts, they actually agree. And then again, you view an arrow such a triple as pointing from X to Y. Yeah, so these two classes of examples, I mean, so this last example has all sorts of generalizations. So this is G2. 2 remembers the number of letters, so just 0, 1, but you could also look at n letters, and you could look at certain subshifts. So this gives rise to a family of groupoids. And yeah, so both of these come from sort of classical dynamics, if you like. And in both of these examples, you see the idea behind the groupoid that it's a structure that allows you to study the orbit space of your dynamics. Yeah, so in the first example, you connect 2 points if they lie in the same orbit. So X and gamma X are typical elements in the same orbit. And also in the second example, you connect points in the same shift equivalence class. So that's the idea. Yeah, I should mention operator algebras at some point, so I do it now. So as we know, these groupoids give rise to operator algebras. So for instance, for G2, if you apply the groupoid C-star algebra construction, you would get the Kunz algebra O2, and you can also do it for the subshifts, and you get Kunz-Krieger algebras and so on. So this gives us C-star algebras we like to study. Yeah, and I mean, in this talk, you won't see many operator algebras, but so at various points, I will point out that the ideas actually come from operator algebras. So that has been a source of inspiration, if you want. Okay, so these are examples coming from dynamics, but I want to somehow view these groupoids as dynamical systems themselves, so general groupoids. And to explain why this is a valid perspective, let me explain the following. So there is a certain class of groupoids singled out by this condition called étal, which says that you have certain subspaces, which are called bisections, and you want these open bisections to generate the topology. So a bisection is just a subspace sigma. So sigma is a subspace of G, and then the condition is that both the source and range restrict to homeomorphisms of sigma onto the image of sigma under S and R. In addition, you want also that these source and range, these are subspaces of the unit space, that these are actually open subspaces. Yeah, so another way to think about this is that R and S are local homeomorphisms. And yeah, so if you have this notion of étalness, then in a sense, your groupoid induces some sort of generalized dynamics. Because if you look at this diagram, what happens is you now have these two open subspaces, source and range, and you can go back with S up to sigma and then go down with R to connect the two subspaces. So what you get is a local homomorphism which is only partially defined, but from some open subspace of the unit space to some other open subspace. So this is the beginning of a somewhat generalized dynamical system, because you not only get one such partial homeomorphism, but you get a system from your groupoid by looking at all these bisections. And you can check that actually you get what's called an inverse semigroup. So you can multiply these homeomorphisms, these local homeomorphisms. You can form their inverse. And so, yeah, in a sense, this gives you an action by local homomorphisms on your unit space. So every groupoid gives you this, and in some way the groupoid is determined by this system of local homomorphisms. So that's why you could view these entire groupoids as giving you a generalized dynamical system. Okay, and the last condition I need to come to topological full groups is this one. This groupoid is called ample if slightly stronger you have a basis of compact open bisections. So this is somehow saying that the unit space is totally disconnected. So it's zero-dimensional. And the reason we want that is because, so I mean, you'll see it in a minute, but to define topological full groups, what we do is we take these partial homomorphisms, and we want to piece them together to global ones. Now, this piecing together requires you to sort of cut and paste. And this might, in a general topological space, might lead to some obstructions that you cannot always do that. But if you have totally disconnected spaces, then you can always cut and paste and piece these local ones together. So this is the idea why we want ample groupoids. Okay, so here is now the definition. So topological full groups. What is this? So you have an ample groupoid, and then you look at the bisections as in this picture, which are global. So in the sense that both the source and range are equal to the whole unit space. So they are as big as they can be. And these form a group because if you have two such bisections, you just form pointwise their product using the multiplication in the groupoid, and you check that this again gives you a global bisection. Okay, yeah, so that's a definition, but it's a bit fishy. So one problem with this definition is if you ask for this condition, so you want compact open bisections with this property, then this automatically forces the unit space to be compact itself, yeah, being the image of a continuous map. So in general, you might want to avoid this restriction. So this definition I showed you really is only for compact unit spaces. And in general, what you do is you take a limit. Yeah, so you restrict for each compact open subspace of the unit space, you restrict your groupoid. So look at arrows that point from and out of your compact subspace. This restricted groupoid automatically has compact unit space. So you apply the definition. And then you can always, if you have a smaller compact subspace in a bigger one, you can always embed the bisections. Because what you do is if you have a smaller bisection, just going from U to U, and you want to get a bigger one covering V, you just add the complement of U inside V to be able to cover everything, every element in V. Yeah, so there's a canonical sort of inductive system you see, and this gives rise to this limit of the groups. Okay, so that's the definition of topological full groups. And yeah, let me show you some examples.
Sorry, I have a quick question, if I could.
Yes.
I'm a little bit confused. So U and V are at the level of objects, yes? G0, and sigma, yes. And sigma is subset of G, yes? So
yes. Yes, so we take this restriction, yeah. So we look at all elements in G which have range and source in U or in V.
Mhm.
This is another groupoid, but this has no compact unit space.
Yes, and this map which sends sigma to sigma disjoint union, yes, with.
Yes.
So I have a problem with this map since sigma is on the level of
Yeah.
morphism.
But you can view this as, I mean, the unit map sends this to an element of the groupoid.
Okay,
It
so,
Yeah, so I
maps
view
is an element
G0
of
as a
the groupoid.
subspace of G.
okay, so you view it like a.
As I said, every object you identify with the identity morphism.
Okay, now I see. Thanks.
Yes. Okay. So some examples. Maybe the first setting where these four groups have been studied is the setting of Cantor minimal systems. So this is a special case of these group actions I showed you, but the group is just the integers. And because that's simply generated, this is really saying you just choose one homomorphism of your space. And so Cantor system means that X is the Cantor space or homomorphic to the Cantor space. And okay, so minimal is just so that I can state the theorem, but minimal means that every orbit is dense. And in this case, if you take such systems and form the transformation groupoid and look at the full group as I defined, then what you see is this coincides with certain homomorphisms of X. And which homomorphisms are the ones which locally agree with the power of your generating homomorphism? Yeah, so the homomorphisms you look at are those that can piece together locally from the powers of this generator, this one homomorphism you chose. So in this case, that's a more concrete description of the full group. And the theorem I want to show you is the one roughly 10 years ago, which sort of generated interest in this class of groups. So Yushchenko-Monod showed that the full group for these Cantor-Memnian systems is amenable. And this was a big result because this then led to the first examples of groups which are on the one hand finally generated infinite simple and on the other hand amenable. So this combination of these two different properties, that was not known that you can construct such groups. And this is for the first time that they were able to find this class of groups. Okay. So, and then, so there are various other sort of similar type results that I want to show you, where these full groups lead to new examples of groups with various properties, solving open questions. So Nikolashevich, he used a similar construction, also full groups, but for slightly different groupoids, to find the first examples of, again, finally generate infinite simple groups of intermediate growth. So this is now even stronger because intermediate growth implies amenable, but it's a very sort of, very special geometric property for the group. Maybe also the reason why I showed you this particular groupoid G2 is because if you form the full group of that groupoid, you get a group that is sort of well known in group theory, and that's Thomson's group V. So it's one of the groups introduced by Thomson. And that was a very interesting example of one of the first examples of an infinite simple group, and has been studied a lot in group theory. There are all sorts of generalizations of this group. So so this already gives you an interesting example, and in a sense it tells you that Thomson's group V and many of its generalizations, they can be studied from the point of view of groupoids. The result I want to show you about V and its generalizations is the following. So this is now in a more algebraic setting, or topological setting. So Skipper, Witze, and Zaremsky, they used variations of V to find first examples of infinite simple groups again, which have very special finiteness properties. So they are what's called type Fn-1, but not type Fn. So this type of n is saying that you can find a model for the classifying space for the group such that its n skeleton is compact. So this is somehow a finiteness property for this for models of classifying space, and this is somehow very precise. It's type fn minus 1, but not type fn. So, and for each n, you can do this. Okay, yeah. So you see roughly the idea why these groups are interesting. So they give you a rich source of infinite simple groups, and then you can sort of, by choosing your groupoids, you can achieve various prescribed properties you're interested in. And previously it was not so easy to construct infinite simple groups, and now you have a rich source of constructions. Okay, so now let me come to the main question for this talk, and that's the question: how can we determine group homology for these topological full groups? So yeah, I mean, group homology is a very, if you want, basic invariant for groups. And so this that we ask this question already tells you that, I mean, although there are these very interesting results about full groups, many things are still mysterious about this class of groups. Yeah, so homology is something that is sort of, if you, whenever you construct a new class, you would like to know. And so that we're studying these basic questions, and what tells you that it's still not clear what we can say in general about these full groups. So computing this invariant is one thing, but also, of course, we want to understand these full groups better. So the hope is that if we succeed in developing tools to compute homology, maybe along the way we also develop a better understanding for these topological full groups. Okay, so now let me first of all outline the strategy that we developed to compute homology. So the summary is so maybe before I come to that, maybe I show you some sort of preliminary results or results that inspired our strategy. So one result due to Matui is actually a conjecture, and so he says that there should be a sequence, a short exact sequence, which tells you something about the first homology of the full group. So he conjectures this first homology projects onto the first homology of the groupoid, and the kernel is somehow controlled by this zeroth homology of the groupoid with Z mod 2 coefficients. Now, maybe I should say briefly, I mean, so the homology of groupoids can be defined in a sort of analogous way to group homology. And there are various perspectives you can take. So you can write down a very concrete chain complex called the bar complex and compute its homology. That would give you group homology or groupoid homology. You can do it more topologically by looking at classifying spaces and computing their homology. Or you can use homological algebra. So you can use Tor functors to compute these homology groups. So this is just to quickly give an idea of this invariant. And so Matui had this conjecture. It's called AH. So A stands for abelianization, because H1 of a group is its abelianization. And H stands for groupoid homology. So it's a relation between the abelianization of F and groupoid homology of G. And this conjecture has been verified for all sorts of examples of groupoids by Matui and also others, Nyland, Ortega, Scarborough, others as well. And I think it's still quite amazing how Matui came up with this conjecture. So I think he just made lots of computations and sort of realized that there should be some relation like this. So this is one sort of inspiration, that somehow there should be a relation between homology of the groupoid and homology of the full group, which is, I guess, natural to expect. And the other result that has been important for us is this result, rather recent, of Simic and Wahl, who were able to compute for this Thompson's group V its homology. And they show that it has essentially trivial homology, so it's acyclic. So, I mean, every group has integers in 0-degree homology, but other than that, they show that the homology vanishes. And so this answered or strengthened the result of Brown, who was able to show that V is rationally acyclic. So if you tensor with Q, then you get no homology groups. And they were actually able to show that integrally you also have no homology. Yeah, so as I said, V is a particular full group for this groupoid coming from the shifted on 2 letters. So this is if you want a computation of a full group, a homology of full group for a particular case. Yeah, but in contrast to Matui's result, this is now in all degrees. So you get the homology in all degrees, not just for H1. And yeah, not only the result is interesting, but also the way they arrived at this result. So they were actually using tools from algebraic topology. So they were looking at a certain algebraic K-theory spectrum they constructed for this particular group V, and then they used tools from infinite loop space theory to complete this computation. Okay, so yes, so this was inspiration for us, and now let me come to our strategy to understand group homology. So yeah, let me in one diagram summarize the plan. So we have these ample groupoids, as I said, and from these we construct these topological full groups. And now what we do is we take our groupoid and construct what's called the small permutative category. Yeah, also other sometimes also called symmetric monoidal category. So it's a category which we will build from the bisections of our groupoid. So bisections are important, and they will be important for us when we construct this category. And crucially, there will be a direct sum operation. So I mean, yeah, I guess these categories they come up, or they came up maybe first of all when you look at rings and their projective modules, they form such a category, and then so you can use that to construct algebraic K-theory for rings, say. And we do the same. So we take our category that we construct from the groupoid, and we construct its algebraic K-theory spectrum. So it's a spectrum in the sense of topology, sequence of spaces with maps and so on. And from this, we can then associate its infinite loop space. So this is a sequence, a spectrum of spaces. The infinite loop space is one space and essentially covers the same information. And now there's this question mark, because we wanted to understand the full group and we did all this. And now you ask, why did we do all this other stuff? So why does it help us to understand the homology of full groups? And yeah, so let me explain the connections. So how is all this related? Okay, so the first result is saying that for any ample groupoid, the homology of the groupoid is always the same as the reduced homology of this K-theory spectrum we constructed. So that's the first link, that the K-theory gives you the same homology. So that's another perspective on groupoid homology. The second result is not for general ample groupoids, but we need some conditions. I will explain in a minute what these conditions are. But then the result is that the homology of the full group is given by the homology of this infinite loop space. Essentially, so I have an index 0 here to indicate that I only look at the component of the base point of this loop space. Okay, so maybe I first explain these conditions. So there's two conditions, minimal and comparison. And then I'll tell you a bit what the idea is, why these two results help us in what we do. Okay, so minimal just means, as before, that every orbit is dense. So orbits in the groupoid setting are just this. So you fix a point and you look at all arrows pointing out from that point. You collect the ranges, and that's the orbit. So every such orbit should be dense. Comparison is saying the following. So yeah. So you want, whenever you have two non-empty compact open subspaces of the unit space, the following should hold. So if you look at all invariant measures, M of G is a set of invariant measures, and if one of these subspaces has always less measure than the other one, then this comparison says you can find sort of a dynamical explanation why the measure is always smaller. So the explanation is that there is a bisection which transports U into the other open subspace V. Yeah, so if you have this condition, assume you have this conclusion and you apply measure. So being invariant precisely means that source of sigma and range of sigma have to have the same measure. So this condition immediately implies that the measure of U should be less or equal to the measure of V. Yeah, so in a sense, you always have the reverse implication, but the comparison says that actually these two things are essentially equivalent.
Sorry, is this for a given measure, all possible measures? Or?
This should hold for all. So if you have this inequality for all non-zero measures, then you have this dynamical way to relate U and V.
Yeah, it's the for all is there. I'm sorry.
Yes. Yes. So yeah, so it's an interesting property, this comparison. This is one point where the idea comes actually from classification of C-star algebras. So this is a notion that is used in the classification program. And up to this point, we don't have an example of a minimal ample groupoid which does not satisfy comparison. So it's interesting, but in a sense also mysterious. Okay. So yeah, so these are the conditions. And now what's the idea behind these two results? Well, the idea is, you want to understand homology of this full group. And what we know, what we can compute in many situations is the homology of the groupoid. So you use these two results to pass to the right-hand side of these identifications. And then you're in the world of algebraic topology. And then the question really becomes, can you express homology of this infinite loop space in terms of homology of the K-theory spectrum? This is somehow the known data. This is the one that you want to understand. And this question, this is sort of, I guess, natural and has been studied by people in topology and homology theory. So we can sort of use their tools to answer questions that we're interested in, to try to describe this homology of the full group. So that's roughly the idea. And let me show you some consequences that you can obtain from these results. So yeah, let's assume that we have groupoids satisfying these conditions for the second result. So we have both results and can apply. So for instance, one thing you can obtain are these vanishing results. So if your groupoid homology vanishes up to a certain degree, then the homology of the full group has the same behavior. So it vanishes also up to that degree. And in top degree, the homology groups will be the same. So in particular, you can apply this for the case k equals infinity. And then the theorem says if you have no groupoid homology, then your full group is acyclic. And so this explains this computation I showed you, that for Thompson's group V, you get that it has no group homology, because the corresponding groupoid is G2. And this corresponds to the Kunz algebra O2, and we know that its homology vanishes. I mean, one way to see it using similar arguments is that the K-theory of O2 vanishes. So that's an explanation for these computations of Simic and Bar. But you immediately get all sorts of other examples. So for instance, if you take this groupoid G2 and you form a product, direct product with any other, say, minimal amper groupoid, then this new groupoid will also have trivial homology, groupoid homology, and hence the full group will also be acyclic for any such product. So this gives you a large class of acyclic full groups, for instance. Second result is rational computation. So as usual, rationally things become easier. I mean, ideally you would like to have a recipe where you input the groupoid homology, and as an output you get the group homology of the full group. But in general, integrally, this might be complicated. But rationally, you indeed get such a formula. So the rational homology of the full group, you have a formula here where you look at the odd degree groupoid homology, again rational. You form this exterior algebra, and then you tensor on. You look at the even degree homology in this symmetric algebra.
So, sorry, would you, I mean, there is the thing that if you have a Hopf algebra and you have the primitive part,
yes,
and then you take exterior algebra, you get the whole thing. Is that the kind of thing that's happening here?
Yeah, that's the thing. So what you see here is some sort of universal enveloping algebra for certain Lie algebra, and as you say, you look at these primitive elements. Yeah. So the result you can use here is by Milnor and Moore, for instance. I think. This is what's happening exactly. Right. So rationally, at least, you have a full answer to a question, and because groupoid homology has been computed for many examples, for instance, for these groupoids describing Kunz-Krieger algebras or graph algebras, for all of these, you get rational homology computations.
So sorry to insist. So the statement would be that the groupoid gives the primitive part, or the homology of the groupoid gives the primitive part of the homology of the full group.
Yeah, so if you want to be precise, I think you have to factor through the homotopy groups. So, yes. So, I mean, rationally, rational homotopy groups are the same as the homology. And then usually this what I said about universal enveloping algebra is about homotopy groups. But then, yes, indeed, the primitive part of homology agrees with the one that you described as groupoid homology, and that gives you this formula. Okay. And the third application is related to Matoui's conjecture. So the application is that indeed we get an exact sequence which has, so the right part is exactly what we saw in Matoui's AH conjecture, and it continues, we're able to continue it a bit more further to the left. So you can continue with the second groupoid homology, and then the homology, second homology again of the commutative subgroup of the full group. So in particular, this implies Matoui's AH conjecture for this class of groupoids. But also, I mean, when Matoui first introduced this conjecture, he actually thought that this map here from H0 to H1 would be injective. So in other words, you could extend by 0 on the left. And later on, they found counterexamples to this stronger version. And then this a longer sequence gives you an abstraction for this map to be injective. So this gives an explanation for these counterexamples.
Is this the kind of sequence that comes from a spectral sequence?
Yes, yes, very good. So yeah, so maybe I should mention this. I mean, I like this story sort of. So yeah, this is well, you can derive this using the Atiyah-Hirzbruch spectral sequence, using the results that I showed you. Because yeah, so this thing here you can interpret as first homotopy group, and then this is a spectral sequence that computes homotopy group using homology in the homotopy group of the sphere spectrum. And well, you see now, so this is a consequence of the Atiyah-Hirzbruch spectral sequence. And so by looking at that, yeah, I think Matui can be very happy about the way he formulated his conjecture. He's named his conjecture as the AH conjecture. So this is coincidence. Okay, so that's, these are the consequences. And now I guess I can talk a little bit about ideas. How long should I go? Maybe 5 minutes or something? Okay, I'll just continue forward.
5 minutes are fine, then if you take, but then it's not a big deal either.
Okay, so I say something about the ideas then. Right, so yeah, maybe the most central question is how to construct this small permutative category. So the idea is this. So we really want our bisections to be the morphisms in our category. So the objects should be compact open subspaces, and the morphisms should be our bisections. This is the basic idea behind this category. Problem is, as I said, we want to be able to form direct sums. So how do we make sense of this operation? So there is a sort of easy case how to make sense of it. If your two bisections are completely disjoint, yeah, then your direct sum would just be the disjoint union. So this is somehow the natural thing to do. In general, however, you could have bisections which have some overlap, so you have to worry about how to form disjoint unions. What does that mean? And so the way out is the following. You just create more space. Yeah. So this is, I guess, in K-theory, yeah, natural idea. You stabilize or amplify, yeah, whatever you want to call it. So precisely, what we do is we don't look at subspace of the unit space, but we create infinitely many copies of this unit space. And then the bisections are not the ones in G, but we created this space, we sort of make it disappear again by connecting everything in N with itself. So this is the full equivalence relation. Up to Morita equivalence, we didn't do anything. This is somehow the idea. So that's why we introduced this R. And we look at compact open bisections of this bigger groupoid now. And now it becomes very easy to form the direct sum or disjoint unions, because say if we have a bunch of if we have compact open subspaces of this guy, then this will only have finitely many components by compactness. And if we have another one, then what we do is we just shift the second one so that the two become disjoint, yeah? Because we have enough space. So we just shift by m+1 in this case, and then form the disjoint union of these spaces. And similarly for bisections, by compactness, it will just sit, any bisection will just sit in a finite part of the groupoid, and then you can just shift to make a disjoint, and then you just form disjoint union.
So you take the additive category, universal additive category, but don't you want like to define it, to mod out by saying that, the sum of U and B is the same, as a disjoint union when they are disjoint?
Yeah, so this will be sort of by construction, more or less, because you will have isomorphisms if you have disjoint union. So you can, up to isomorphism, this will coincide with the actual set theoretic disjoint union if you can form one. So this is taken care of by this.
Okay.
Yes. Okay. Yeah, so this is really the crucial idea. You form these small permutative categories, and then, as I said, you use the machinery, algebraic K-theory machinery, and produce the spectrum, so this sequence of spaces with these connecting maps between the suspension of one space to the next. And so in our case, this is a sort of a special kind of spectrum. So it has this property, sometimes called the omega spectrum, but only in positive degree. So the n space is up to homotopy the same thing as the loop space of the n plus first space. Yeah, but only if you go from degree 1 on. And so this is one way to introduce the infinite loop space. So what you do for degree 0, you might not have this. So the infinite loop space is just, in a way, enforcing this. So in degree 0, x0 would have to be the loop space of x1. If you don't have it, you just declare that to be your loop space. And then, it's the loop space of the loop space of x2, and it's a loop space of a loop space of a loop space. So this is, the name infinite loop space.
Your K-theory is such that the spectrum is always connective, right? Has no negative homotopy groups, or does it?
Yes. Yes. Okay. Right. Yeah, and then so these are the basic objects from topology, and then we apply. We use the two results I mentioned to get the consequences. Okay, I think I'm basically out of time. I mean, I have some things about the theorems, but let me just finish for now. And thank you very much.
Okay, thank you, Xin, for a wonderful talk. Well, I already asked lots of questions, so let's see what the rest of the audience has to say. Let me see. Is there anything in the chat?
So Willie, can I ask a question?
Yeah, sure. Please
So
do.
Xin, so you focus on computation of homologies. So how about the cohomology? Is there any computation or any conjecture toward it?
I mean, I guess once you have homology, you can use sort of general tools to get results about cohomology by using, universal coefficient theorems, these kind of things. But directly, it's not so clear because, so I'll show you a little bit. So one thing we use is this group completion theorem, which has something to say about the homology of infinite loop spaces, and that I don't know about the virgin cohomology. So that's why these results initially are homology, but then you can use general tools to say something about cohomology.
Thank you.
One little question. I mean, there's this other conjecture of Matui relating groupoid homology with K-theory.
Mm-hmm.
Do your results say anything about that?
Oh, about the other HK conjecture.
Yeah.
Not directly. I mean, this is about groupoid homology, and it would be interesting to understand like connections to topological K-theory for C starters, but so far I haven't really tried to make that connection. Yeah. I mean, yeah, I guess in general, homology is not, I mean, if you want to cover general groupoids, I guess you would need something using Baum-Kohn and so on. Then groupoid homology is maybe not quite the right thing. You need a bit more like different type of homologies, but yeah, would be interesting, but I haven't really looked into that yet.
Would you show again the
Yes.
slide where you give the definition of the category B, the symmetric monoidal category B?
Yes.
It's not there.
Yeah,
there. Okay.
I mean, it's not,
Yeah.
it's just the idea. It's not the precise definition, but yeah.
Okay. So
Mhm.
this is the compact open bisections. So the semigroup associated to a certain groupoid,
Yes.
like the amplification of the groupoid.
Yes.
Yeah. So it's kind of Morita equivalent to the groupoid, so to say.
Yes. I mean, you can describe these bisections as also in terms of the original groupoid. These are just finite collections of bisections and they have to match up source and range somehow. I mean, you can write down explicitly what this is saying. Yeah.
So this would be like a kind of K-theory spectrum of the so-called Steinberg algebra of the groupoid without the coefficient ring.
Yeah, I mean, it's interesting what the precise relation is. I mean, the Steinberg algebra, if you just look at it as a ring, then you would look at modules over that ring somehow, right?
Mm-hmm.
And it feels to me that this category only looks at certain modules, which are somehow,
Yeah,
So
but that's why you remove somehow it's a definition
yes,
over the field with one element.
yes,
Because you do not put any coefficient ring. But this should be related to somehow, I mean, that if you put together this spectrum and the K-theory spectrum of the, say, ground field, and you combine it in a certain way, then you should obtain the K-theory of the Steinberg algebra somehow. I mean, this.
okay, yeah, that would be very
vague
interesting.
enough. But it's vague enough conjecture that in some form it might even be true.
Yeah, I mean, there should be a connection because we know that like the homology of the groupoid can be written as Tor of the, Steinberg algebra with coefficients of the unit space and so on. So, and that comes up here as well because the homologies agree. So there should be a relation, but the precise statement is to be found.
Okay, so do any of the other participants have questions?
Sorry, I have a question.
Raise hands. Yeah, Adam Bigger has a question. Yeah.
Yes. So at some moment you mentioned that there is no known example of an ample groupoid which is minimal and has not this comparison property. So is it reasonable to believe that there is no such example at all? Or you expect that there is some example, but it is only very hard to find it?
Yeah, this is a good question. I don't know. It depends on who you ask, I guess. I mean, if it's true that every such has comparison, then this would be good news for the classification program, I think, for C-star algebras, because then you get sort of more groupoid C-star algebras that you can apply classification to. I think some, in dynamics, some people believe it should be true that every, because these groupoids are in zero-dimensional spaces, so this somehow dynamically is sort of very low-dimensional situation, and it should be true that you have comparison. But I don't, I don't know. No strong feeling either way.
I see. Thank you.
By the way, in the particular case of the groupoid associated to a graph, say the graph with one vertex and n loops, when n is not necessarily 2. Is it clear what the relation between the K-theory of that, of your category B, and the K-theory of the Steinberg algebra is?
Yeah, I'm actually not, I mean,
many believe if n is 2, they are both 0, right?
Yes, but is there like has the K-theory for the Steinberg algebra been computed, or what's the status?
Well, the Steinberg algebra is the Leavitt path algebra, and this is computed in terms of the K-theory of the field.
Okay.
So if it's ON, if it's the analog of ON, which we call LN, so you get K-theory with coefficients of the field with coefficients in Z mod n minus 1.
And then what happens if you take like the integral version of that algebra? I mean, that would be sort of the analog here, I guess.
Integral, yeah, the same.
Okay, same. Okay.
You replace field by integers.
Okay.
So this holds on any sufficiently regular ground ring.
Yeah. I mean, there should be a relation. The formulas, I think, will look the same because you sort of you get the formula for homology using like the usual one way to look at these graph groupoids, and this applies here as well. So yeah, I mean, at least from the point of view of formulas, there's some similarity, but I don't know like a direct connection.
Okay. Okay, that's all on my side. So if nobody else has any question, I think we can stop here. Xiang.
Okay, thank you very much.
Very nice talk, Xin.
Thanks.